Right, this video is going to be about having a better understanding of your dim bulb tester, the humble dim bulb tester that you can easily build for yourself, which I suggest if you're going to be working with any kind of mains device that you're playing with to repair or something like that, especially valve amps and valve radios, that obviously I'm assuming COVID generated a lot of interest with people being stuck at home and having things to do and looking at playing themselves with electronics gear, which is great to get people involved, although probably many people may not have, even a basic formal electronics education or knowledge, and which is fine because you can learn an awful lot off YouTube, and that's wonderful, but it might help people to understand what a dim bulb tester is and a bit more about how it works behind the scenes, because it's not quite straightforward. They're a really safe addition to anybody's desk, especially for people who haven't got a Variac, which is what I used it for in the last video, testing a valve radio. And there's an example. Well, first of all, why would you want one? Well, the example of a valve, say an old valve radio, could be old granddad's left in the loft for 50 years. People have found it, you know, and gone, oh, let's have a look, let's plug it straight in. Of course, this is one of the worst things that you can do to any piece of old equipment, because the capacitors may, you know, they'd be old and probably need replacing. And the worst case scenario, one of them is that, well, it probably might give you a fright if it goes pop, may even start a fire. But usually it just makes a mess, especially if old valve amp radios and stuff have got paper capacitors in them, because I know, because I've done it many years, or not many years ago, a few years ago, and just impatient, didn't even bother building one of these, which is really simple to do, which I'll talk about in a minute. Blew the paper caps and it just made a real carbon mess inside of it, so if you wanted to repair it after that, you've just made a mess. And of course, you've broken the amp to a worst case of what the condition that it was in when you found it. So this is, you know, a really bad thing to do for people who don't know, who find old valve radios and just want to know if it works, and they go and plug it in to find out. It's not a good idea if you value that radio and you want somebody who's qualified or to be able to fix it for you without making things worse. And the other worst case scenario is, let's say the filter capacitors at the on the mains transformer do actually go short, and you plug it in, you might actually pull way too much current through the mains transformer and burn the mains transformer out, and that's the most expensive piece of kit to replace, if you can even find an equivalent. In most cases, that's the most expensive. So you've really ruined things by just plugging it in to find out. If you use a dim bulb test, there's no guarantee that it might not still damage the unit, but basically what happens is, the base case, the worst case scenario is plugging in a piece of equipment, unknown piece of equipment, that has actually got a short in it because of either, you know, a shorted mains capacitor because it's failed, or a connection to the chassis or something like that. This plug mimics that by having just a connector between the live and the neutral pins, and so it's basically shorts out this plug. So just in this case, this would mimic exactly what a shorted old bit of equipment that you're firing does, and basically if I plug that in, by shorting it out, it completes the circuit. So what we've got here obviously is, up to this point, this is a normal extension lead plugged into the wall outlet, 240 volts across it, so this effectively mimics a normal wall outlet. I've got a power meter plugged in here with the dim bulb circuit running away from this. So this would be the equivalent of plugging this into the wall at this point and being able to read the power of this bulb, which, as you can see, it's a 25 watt bulb and it's actually reading 25 watts thereabouts. Now, up to that point, everything straightforward, easy enough to understand. So how do you actually make one? Right, let's just switch that off a second. Really simple. You can get the basic bits from any hardware store. It's just or find, you know, from an extension lead. I think I stole this from an old extension lead that, and just split the insulation with a just a knife, cut a section out to expose the three connectors that we have here in the UK. We have the earth, the live and the neutral, and in this particular case I wired it so by just cutting the live cable, the brown, and stripping the ends and then screwing them into the bulb holder that connects to both of those pins. Then wiring it up as normal here, so the live would continue on to go to the appropriate live pin on the socket, which in the UK, if you're looking at a plug in this direction, the live here is on the left, so you'd be wiring it this way round. The live is this pin on the bottom right, so that would mirror that way. So that would be the live here going back through the bulb. I bolted it to this fairly sizable piece of wood that I found in the shed to give it a bit of weight, so it's not going to fall off a table too easily, and some grommets that I got from a local hardware store just screwed into the wood to make it nice and stable. Okay, so what would you use it for in terms of, as we just explained? It's to test old bits of equipment that may be shorted and to limit the current through them, so you've got a better idea of whether or not they're working at all. And then what you do is you put the lowest wattage bulb that you have, and which over here we have these sort of lamp bulbs that are 25 watts at 240 volts. Now this is the lowest value that I have got, and it's usually ample. And so what is the actual current that would be drawn by a 25 watt bulb? I'm going to be using, there's two equations in electronics that are used a lot, and one is for power, which is a product of the current and the voltage in the circuit. So in the UK, the voltage would be 240 volts mains, which is an RMS value. It's not the peak value, so always be aware of that as well. There's a much higher value. 240 volts RMS is actually equal to 339.5 volts peak. Then power is a product of those two. And then we have Ohm's law, which is where the voltage across the circuit is equal to the product of the current multiplied by the resistance. Now, you might assume, just by looking at a basic circuit, and see these as two equal resistances with the same voltage across the two, like a resistance divider. Well, it's not that simple because they're not linear resistances. Bulbs are not linear. And I can show that to you with just the bulb that's actually in here. If we measure the cold resistance of the bulb, we can see here that, if I can hold this on somehow, we can see that, let's just check that's right, so down to 0, it's showing about an ohm because of the bad quality leads. So we can see with this this is a 25 watt bulb, it's showing about 165, less the 1 ohm of the resistance, so about 164 ohms cold resistance. Now, if you take this one for example though, this is a lovely big 150 watt bulb. Now this has got very different resistance when it's cold. It's only 21 compared to 164. So the significance of that is that they would pull different currents for a very, very short period of time. If we did using Ohm's law, where V over R is equal to the current, we'd have 240 volts across the cold resistance of this bulb. The moment that you switch that circuit on, that might give a surge current of about 1.5 amps, which is why the bulbs actually probably, even if you notice them, they'd actually go as bright as possible because they're pulling a maximum amount of current through the circuit until the actual filament gets hot. Then when the filament is hot, it actually increases its resistance, and it's actually in a non-linear fashion that works, which is basic principle of the whole circuit and why it's very, very useful as being a form of protection for limiting current in a circuit when it's used in series with the device that you're trying to test, because the bulb will tend to take what current it requires to fulfill its resistance needs and therefore limit the voltage and current that's left at the output, as you've seen by me shorting it out. the bulb can only then have its normal maximum operating conditions, which is 240 volts at whatever current it pulls with just the bulb on its own. So when you plug a device in, that current is now limited by the maximum value of the resistance that this bulb gets to. And this massively limits the current that's available through the unit, which in the worst case, if it was a short, it would still only limit the current to a safe value. So that's its basic principle of operation. So if you do the calculations for that particular value to give an idea of what the current surge might be, that initial plug-in and turn on of a bulb, it might be pulling, although it's rated for 25 watts, it could actually just be for a very, very short period of time. If it's pulling, if you do the calculation, it could be pulling around 350 watts instantaneously. Whereas once it's actually got hot, and then you do the calculation for the bulb resistance, which I'd worked out earlier for a 25 watt bulb. If you use the power equation of P equals IV for a 25 watt bulb, you will get its hot resistance running at only 0.1 of an amp. So you can see there's a big difference between the surge current value of up to 1.5 amps instantaneously to once it's actually settled down and only pulling 0.1 of an amp. Now, we can now use this equation to get an idea of what its resistance is when it's actually full on and hot. And you can see it's gone from the 164 ohms that I measured for the small bulb when it was cold to now settle down and only pulling the 0.1 amp, which would then give a resistance value of the hot bulb at 2,300 or so ohms. So you can see there's a big difference between the cold resistance and the hot resistance, and that's basically due to a concept of the way the power works in a circuit with resistance. I'm not going to go into this in detail, but suffice to say I'll put an Excel graph and I'll go through some of the numbers so it makes sense. I'll put a shot of a graph in a minute, but it'll give you just to show the non-linearity of current through a bulb. But it's got to be an incandescent bulb. You must remember that if you build one of these LEDs, so they're no good. You want the resistive capabilities of incandescent filament type bulbs. You know, whatever, don't know whatever they're made of, tungsten or whatever it might be. But basically, this power equation has a relationship to current that's not proportional. It's a square law, which means it's exponential. Because if you do, just to try and explain that for people who are interested, and if you're not, don't worry about it. But because V is equal to IR, which is your basics of Ohm's law, if you substitute the values of voltage in the Ohm's law equation into the power equation, which is a product of voltage multiplied by current, then you would have P is equal to, because V is equal to I times R, you've already got I and R together as this value here as V. So this would then become I times R for an equivalent power equation. So it becomes I squared R. So you can see that an increase in power is represented for a fixed resistance by the square of the current running through it. So it's not linear, and that's basically really why I'm doing this video, because it just helps to understand what you're doing when you're putting bulbs in of different power. They're not moving up linearly as most people might expect. They're actually reducing the resistance in a non-proportional way. So the higher wattage bulb you put in, you're reducing the current, sorry, you're increasing the amount of current that can then flow to the unit under test, which is why the lowest power bulb does the most current limiting, which is why you would start to test an unknown device on the lowest wattage bulb, because it only allows the least amount of current to flow through. And I've written these out, and I'll show you a graph in Excel to make it a bit more clear visually. I'll put that in the video. I've done that. Obviously I can't show you, I haven't got split screens or anything. But so I've done calculations here for 25 watt bulb, which we've already seen, just on its own. And it pulls about 0.1 of an amp. A 40 watt bulb pulls about 1/8 of an amp, which is 0.125 amps. So you can see it's not much of an increase between, it's not double, which some people might expect. You might say, oh, 25 watts nearly double, 40 is nearly double, so it should pull twice the current. No, it's because of this non-linearity of the resistance of a hot bulb. It doesn't work like that. So this has only gone up to it's only gone up 20 milliamps between a 40 watt bulb and a 25 watt bulb, even though a 40 watt bulb is near enough twice the power. And then the same again, we see if we now use a 60 watt bulb and do the calculation, 60 watt divided by 240 volt gives a 0.25 amp. So now that's coming on, that's actually nearly double a 40 watt bulb. So you can see the current drawn by a 60 watt bulb is nearly double than the 40 watt bulb, and was certainly double a 25 watt bulb. But it's actually pulling more than twice the power of a 25 watt bulb. And then as we go up in bulb values, it becomes exponentially even more. So a 100 watt bulb, if you do the calculation, is actually 0.4 of an amp. So this is a 100 watt bulb is pulling 4 times the current of a 25 watt bulb, and that happens to be sort of a linear relationship. 25 watts is 4 times smaller than the 100 watt bulb, so that actually does correlate. But that's just a trick of the actual numbers. A 150 watt bulb now goes up, which is now 6 times the amount of power of a 25 watt bulb, and it is actually pulling 0.625 amps. So when you see though on the equation, it's not actually linear the way the current actually flows. So it's not exact. It is actually the higher you go up in wattage of the bulb, the much higher the current there is that's allowed to flow through a circuit. So I'll put that up in a minute. So we've covered the cold resistance. Now, to show you this non-linearity and the way that impacts this relationship between the current of I squared, the I squared R relationship, and power. If we can show that by putting the actual lamp that's got a 25 watt bulb in and a 25 watt bulb in here, and now if we put this on and turn both on, you can see, well, you can't see on the camera because it's not, the camera just looks bright, but I can see the filaments in both of these because they're that much dimmer than obviously a single bulb, because the current, the voltage is being split. But if we look at the power, you can see this non-linearity effect. We know that one bulb took 25 watts, so people might think, oh well, 2 in, it would be taking 25 watts each, but of course they're in series, they're not in parallel. So you've less than halved the actual current that can flow through, and this is what this dim bulb device is actually for. It's to limit the current, disregardless of what value is here in terms of the resistance if it was a short, because the device was faulty. So at least it's limiting the current, and of course it's actually dropped now to about 18 watts for 2 bulbs for 2 25 watt bulbs. So you can see it's massively reduced the amount of energy that's drawn by the circuit. And we know from Ohm's law that any 2 resistances, now that these have settled down, will cause a voltage divider between the 2 bulbs. So we'd expect then to have what was 240 volts is 240 volts across the whole circuit. We can have 120 volts between each one, and we'd be drawing the same current through each one. And if you don't, hopefully I've explained it well enough that you'd have to accept that 2 equal resistances in series will split the voltage, the applied voltage, in half to have the same amount each. So if we actually do the calculation for that, we know that 2 equal bulbs is actually drawing, let's call it for the sake of the maths, 18 watts. I've already done it here. So we know that there's only 0.075 amps. And as we saw earlier, one bulb drew 0.1 of an amp, but now we see 2 together, actually in the circuit, they draw 0.075, so they're only drawing 3/4 of total amount of current between 2 of them of what one bulb was. So again, to reiterate the non-linearity, it hasn't halved the amount of current flowing, which you'd expect if there was two bulbs. They're splitting the voltage equally, but they haven't split the current equally. There's actually 3/4 of the current flowing, not half the amount through each bulb. It hasn't dropped to just half the amount of the 0.1. It hasn't dropped to 0.05 amps. It's dropped to 0.075, which is actually halfway between those two values. But of course we do get, so if we did the calculation, we would see, using the power equation, and let's assume that both bulbs are dropping half of this total value of 18 watts to 9 watts each, and they're just only burning 9 each, with the fixed current that we've calculated at 0.7 amp, you would 0.075 amps, you find that one bulb drawing 9 watts would actually have 120 volts over it, which is what you'd expect because it's half of the 240 volts. I hope that's kind of clear, and I hope that helps you understand what's going on in the dim bulb circuit and why increasing the value, which we can start to do now. So what I'll do, just so you can get a kind of a visual on what happens, is I'm going to change the bulb values and go through them as I did on the in the real world, bringing power to the radio the other day when I was testing it and bringing it up slowly. And the reason you might want to do that is sometimes just to test an amp. If you're going to test something at all and you're not sure of its condition and it is old, you may, if you start with a really low value bulb, it sometimes gives the old capacitors inside the unit a chance to reform to a degree, so they start to work. And I think I mentioned on that video that I allowed the first test, when I plugged it into the mains, allow it to sit for say 15 minutes. If it is actually working and it hasn't shorted or blown anything by plugging it in, if you're that impatient that you don't want to just look inside something, you do want to just know its state, at least try and do that if you can. And put it on a dim bulb tester and at least let it sit there for a while, because there's a good chance then that the capacitors may reform just temporarily or even longer term, long enough to actually have the unit actually allow it to be able to be functional, to be able to raise the voltage in stages without overstressing the components and actually having that initial surge of just plugging it straight into the mains with no tests to actually work to a degree. So I'll go through these bulbs and you can see the effect they have on what would be the device under test by having a higher value bulb in each case. And we'll see the effect on the amount of power and how it looks by changing the actual value of the dim bulb that you're using and going up in stages between a 25, a 40, 60, 100 and 150, which are the common values that we get here in the UK for normal sidelines. Right, so what I've done is I've put the 150 watt bulb in the light. This would represent, say, 150 watt big power amp or something that you're testing. It's in an unknown condition or whatever, and I'm using the 25 watt bulb as the maximum current limiting, which would be the first turn on for this big device that we don't know anything about, a nice big old 70s amp or something. So you can see the 25 watt bulb takes all of the current that it needs, because this represents, the 150 watt represents effectively a short circuit, because it's got much lower resistance than this bulb. So all the voltage and the maximum current that this 25 watt bulb will consume is dropped across this bulb. So the bulk of 240 volts goes across this bulb, leaving almost nothing left to the lower resistance here, because it's closer and closer to a short circuit, so just a piece of wire. So that's how the 240 volts from the mains is dropped totally against this, and therefore this representing a near short, which is your piece of equipment that's got a fault, means that practically no current, very low current, flows through the whole circuit, including this device, effectively keeping it safe from further damage. So I hope that kind of makes it clear. So if we write them down, we can see that with the 25 watt bulb in as the dim bulb, we can see that it mirrors exactly only what's being drawn by this bulb. the power meter is seeing only 25, just over 25.6 watts, just the value that this bulb wants to take for itself as current, totally limiting your device under test and keeping it safe. So let's go through them where I find my pen. So let's put the total power in the circuit there. So I put 2018 there. It's I'll graph these in a minute. So just to see again what kind of the proportionality the power looks like in the actual what would be the device under load. So for the 25 watt bulb here, we've actually got 25 watts, which is what we'd expect. Which is why we use the smallest value bulb that we have, the lowest power value bulb first to test a piece of equipment. So let's move on. So now it's not too hot. So the next value bulb I have is a 40 watt. One done. So putting the 40 watt in as our dim bulb with the same 150 watt load, we can see the 40 watt still pulls pretty much what it wants. It's pulled the 40 watts for itself, and this one's still not lit. So we've got the total power in the circuit at 40 watt. Right, so now we've got a 60 watt bulb in now. Camera's moved a bit, right, but you can see that's still pretty bright, and there's no, just move the light a little bit, move the camera. There's no, if I hold my hand over that, I can just see the faintest of pinky orange on the filament. Don't know, let's just see if that can be seen. No, can't see it with the light off, so that's no good anyway. So again, 60 watt bulb, we're showing 59 watts, so just slightly less than the value of the rated value of the bulb, again being drawn through the whole circuit, and the tiny amount of current that made that glow just a little bit just goes to show that again there's still a lot of limiting done even by a 60 watt bulb, putting absolute sort of minimal current through effectively, you know, a device that was remotely low resistance. Right, for the 100 watt bulb, you can see it's drawing 86. So there's that non-linearity again. And I don't know if you can just see that, but the filament is just lit now on the 150 watt bulb. Right, now I've got the 150, and although you can't tell because of the camera how bright, they are actually sort of sharing the same brightness levels. But two 150 watts, as we saw with the two 20 watt bulbs together, pulls a lot less than what than half. It's 116 watts for a 150 watt bulb. So obviously pulling nowhere near the actual wattage that just one would actually take on its own. So if we graph those results, I'd expect them to see, using these numbers, exactly the same figures as I used for the current, and follow the same kind of non-linear graph. Okay, so in summary, really, the non-linearity only really impacts if you're using the dim bulb tester to test a piece of, especially valve stuff like valve amps or valve radios, because obviously the nature of valves is that they are non-linear pretty much as well, because they only start to conduct when they hit a minimum voltage across them, which is around, let's say they might start to conduct let's say 80, 90 volts DC from the anode down to the cathode inside the valve. And then obviously to be able to really produce their maximum current that's generated, that's evaporated off the cathode, they want to be at whatever the highest voltage that the individual valve is rated at. So they're usually around, for say guitar amps, they usually start around 300 volts, which again, you know, to reiterate the safety aspect, you've got to be aware that you're dealing with, you know, potentially very lethal DC voltages there. But as far as the testing goes, using the dim bulb tester, in summary, really, the thing to note, I'm hoping to get across with that video, the non-linearity of the current as it relates to not just the way the bulbs limit current in the circuit because of that I squared R relationship between current and power. The big step is going to be between, from what we saw there, the 60 watt bulb to the 100 watt bulb, because then that exponential thing really starts to take off and allow much more current and therefore power through to the device under test. And certainly when you get to the 150 watt bulb, it's almost effectively like having it on mains voltage. And if you watch the dim bulb tester video that I did on the Vivlio valve radio, you will actually see that there was a big jump from the 100 watt bulb and the 150 watt bulb. I think the 100 watt bulb went to 160 volts mains delivered to the unit, and the 150 watt bulb was pretty much mains, I think 240 volts or something. Almost, you know, it was, anyway, it was bang on, pretty much mains voltage. Whereas the 60 watt bulb, as we've just seen in this video, the 20, the 40 and the 60 really, you know, they limit quite considerably. So, you know, you could probably cut out the 40 watt bulb, maybe even the 60. If a unit hasn't, you know, there's no smoke coming out of it, there's no reason why it should on the 20 watt bulb, because it's so current limiting that it's just so bright, as if there was a short there already anyway, because, you know, all of the power is dropped across the bulb. So you'd want to bake that unit as long as you can, you know, like just give it that 20 minutes, 15 minutes, half an hour, whatever, just letting it sit there. If no smoke's coming out of it and it seems sort of reasonably happy, and I mean, I like to do stuff through the stages just because of that potential formation or reformation of the capacitors, to see if a unit's going to work or not without further damage, because it just gives that time for the capacitors maybe to reform. And then, as in each stage, they're not just being hit hard with a big voltage across them. That may be the difference between them just failing or reforming enough to be able to handle the charge. And then, like everything else, the more you build on it, the more chance that they've actually had a chance to reform sufficiently to be able to hold full voltage, because it's been done slowly, allowing them to recover a little bit and get up to the full mains voltage. But like everything else, you know, you watch the real professional guys like your Paul Carlson and your X-Ray Tony B's, you know, it's always just best you do a visual inspection first, particularly of the mains filter capacitors that come right after the rectifier diodes, because they're the ones, as I said, can pull as much, you know, most current. If they fail short and they pull a load of current through the secondary winding of the mains transformer, then, you know, you've possibly blown your transformer, and that's a real pain because, you know, it's costly. But really, you should only be using a dim bulb tester with an isolation transformer, because it's really important that you try and get isolated from the mains. And variacs, most variacs, as you know, a lot of the top guys like Paul Carlson will tell you, they are actually linked from their earth connection through to the actual primary transformer. So you still have a potential path to the main circuitry there. There are isolation transformer variacs that you can buy now that are sort of combination pieces that have an extra plug. They have a plug in them, so that, like the dim bulb tester, you know, you'd plug in your variac and it's then use the plug on the side of the variac. but it is actually got mains isolation from your wall outlet. So they are available. So just be aware that if you're going to buy a Variac, buy one of those these days. But older stuff, which is available on eBay, which is still a great units, just be aware that they may not be, probably aren't, the older stuff, mains isolated. And you know, to really be aware that the main change that you're going to introduce to testing a device is when you put in the last two bulbs, because then it's going to have an exponentially much larger current and therefore power going through to your unit, to actually bring it online effectively. So in some respects, I suppose you could think of it that if it's going to fail at all, it will be possibly at the more likely to be at the 100 watt, or certainly the 150 watt bulb stage, where you're almost delivering full mains power to it, and you know and just be aware it's not linear increments. So anyway, I hope you found it interesting, and that it's been a bit more, you know, just gives a bit more of an insight, and to really rate the dim bulb tester, and to see it in that sense of, like, you know, a five step Variac, you know, 25 watt, 40, 60, 100, 150. It's like just cranking a Variac up to those values. The only difference is obviously you'd be turning it off, so you'd let it bake at say 20, and then you'd be turning it off as to change the bulb, so then the whole unit's going flat again. Whereas on a Variac you wouldn't be doing that, because you'd just probably let it sit at say 30 volts. If it was a valve amp, let it sit at 30 volts for 15 minutes, and then crank it up 20, 30 volts, take it to 60, and then 90, and then 150, and 180, or whatever you might do on the knob. But you're not actually dialing it back down again necessarily. It depends how you want to do it, but it's you know, it's just a good way of looking at it. So therefore, for me, it really brought home what a fantastic little device, and so easy and so cheap to build, for anybody who can use a screwdriver.